Perfect. So, as you said, because of our um, performance on the field, we learned some things for the robots to implement it, and we find them very important, and we wanted to share with you today. And we divided in three chapters. We have, first of all, custom drivetrain, then reliable mechanisms, and also cable routing. We'll start it with custom drivetrain, and we think that the most important things to have on a drivetrain, it is structural integrity, to know how to use the space efficiently, and also to know how to make efficient weight reduction. We'll start with our structural integrity.
All right. So, in order to ensure the structural integrity to a drivetrain, we need to take into consideration the two main forces that are applied to it, the torsional and longitudinal forces. For this reason, we decided to develop a custom structure that is lightweight but also rigid. The torsion force is the one that allows the drivetrain to be twisted up and down and can be represented with red. Um, To suppress it, we implemented a plate mounted at the rear of the drivetrain, but also an intermediate plate between the inner plates. The longitudinal force allows the drivetrain to be twisted forward and backward, being suppressed with two plates mounted at the bottom and over the mounters. This way, we created a box that eliminates all the forces that are affecting our robot, and there can be seen there with green in the right. So for the uses of space, one of the biggest advantages that comes with building a custom drivetrain is the possibility to use the available space efficiently, but also creating more space if needed. In this way, the size of the robot can be reduced. In our 3D designing process, we left us fewer empty spaces, making the robot as compact as possible. Also, the modularity is increased, being the fact that when designing, the systems can be implemented easier on the drivetrain.
And also, if you can see on the right, in the right photo, we have an idea of a drivetrain that we designed in the off season, which has a 90-degree transmission with gears, in order to put our motors from the drivetrain into the side of it, to um, reuse the space between the two sides for the more efficient transfer.
We wanted for this implementation to have enough space to implement the transfer system between the inner plates, so that's why we designed it that way.
Okay. Also, another method of using the space is also putting holes in the left space on the plates. For example, on our intake support, we have a leftover space that we used for holes because we didn't know that we want to upgrade it later. So if you can see in the left photo, we have these four holes right here that are used for our stoppers because before the Maryland Tech Invitational competition, we didn't know that we needed these stoppers because during our autonomous period, our intake can stop in the perimeter when we are collecting. So these stoppers can prevent that. And to not recut the plates again, we just mounted them into the holes right here, if you can see. And this is a method to use the space more efficiently and also the time. Um, Now we can talk about a little bit about weight reduction because we are finding it very important because the robot must be fast on the field, but also very rigid. So for that, we are just designing the weight reduction, the pocketing, and then we are using some simulation using SolidWorks to apply some forces to know how rigid they can be. Also, to make it very light, the robot very light, we are using a method to make the plates lighter than carbon fiber. If you can see in the right photo, we have our outer plate and made from aluminum 6061 with pocketing, and on the left side we have our same plate but made from carbon fiber. And if you can see on the bottom of the page, we have our mass. It says that our aluminum plate is way lighter than the carbon fiber plate, so that we can reduce also the cost because the carbon fiber is way more expensive. Um, Also, to compare it with the last season, from the power play season, sorry, we wanted to know if it was worth it, the custom drivetrain and all of the pocketing. Because if you can see on the left side, we have the drivetrain from power play, which has less pocketing and also Gabilda structure. And on the right side, it is the center stage drivetrain. And if you can see, it has the space much more efficiently used on the center stage robot. And also we can make upgrades very faster on the center stage robot because of our modularity and the holes left. Okay.
So next we are going to present about reliable mechanisms, and we think that the most important things about them are simplicity and power draws and how to fix them. So for simplicity, we think that when designing the robot, for most of our mechanisms, we try to have in mind to keep it simple and straightforward principle. This way, being easier for us to iterate our systems, to optimize them to maximum consistency, and do their maintenance. Having straightforward systems make their utilization and implementation into the tier-up and autonomous period more reliable and accessible. So in this photo, we have our crow, and the crows themselves are attached to the main plate with only 4 screws, and that allows us to do their maintenance very easily and change them in case of a breakage. For power draws, we took into consideration the fact that this season requires a variety of systems that they can also do their task efficiently, and we need to fix them in order to have maximum consistency. So, for our motors, we decided to use them efficiently, and this way, when we are not using the motors and reach a certain position that we want to keep at them, we kill them and only engage them after that position needs to be changed. Another solution that we have implemented is using over-center linkages for our servo motors. Over-center linkages have 2 stable positions maintained by a mechanical block. In these positions, the pressure on the servo motors is diminished and they don't consume power anymore. For instance, this season we have never broke a servo motor, keeping the lifespan of the servo motors. And in these photos, we have the implementation of over-center linkages in our transfer systems and in our CRO.
Okay, and the last chapter, and I think this is the most important chapter of all, is cable routing, because it's very important to have protected cables on the robot to not have technical problems during matches. And also, it is very important to know how to make the cable management and how to think about cables from the CAD. So, um, first of all, we have many organizers and cable protections for most of our cables. In the left photo, we have our power play robot and the cable management. We had the expansion hub on the bottom of the robot, but in the front, and all of the cables were protected by the plexiglass plate. On the right side, we have some organizers that we are using for our cables because if a cable is moving and it is forced by movement, the cable protections are uh, protecting them from not tearing them apart and break. Um, Next up, we are also using the pocketing. I forgot to mention that also pocketing is very useful when we want to do the cable management. If you can see in these photos, in our center stage robot, we are using the holes from the pocketing to make the cable management much more protected and also clean. We find out that if you are using go build a structure and less pocketing, it is way harder to do the cable management because you need to think for the holes where to be put for the cables. When you are using pocketing, I mean way more pocketing, it is easier to maintain the cable management, and also it is very accessible. Another thing that we added on our robot, because of its extension, we made a linkage from beams from Gobilda, and on that linkage, we attached the cables from our intake system, and all of the cables are protected by um, um an organizer that is very strong and can and it doesn't let the cables move or break. Um, and in the last part, we want to mention that on the CAD is very important to think where to put the cables and how do you want to make the cable management. So if you can see in these photos, we have an example of a hole from the cable, and on the left side is the CAD model, and on the right side is the real cable from that intake part. And it is very important to have the system same as the CAD project to be sure that the cables can be put exactly the way you thought on the CAD. But even if you have a very uh, good CAD, it is very important to know that there can be cables that you don't know how to place them and you don't know where to be put. And you need to let a little bit of space for them to be uh, kind of protected. Um, so in conclusion, they are very much things to consider when we are building a reliable robot. But I think the most important part is doing the CAD for the robot and to think for as many problems as possible. And we also want to thank the Technibots for inviting us to the FLYSET event. And if you are having some questions, we can ask them, and we are here to answer them. So we received a question.
Oh,
Um,
sorry. I think I was unmuted. So we have a few questions in the chat. So what material is your drivetrain made out of?
so our drivetrain is made out of aluminum 6061, and it is 3 millimeters. The width of the plate is 3 millimeters.
Nice. So when designing drivetrains or holes for screws and bearings, how much tolerance do you want to add to ensure that parts will fit when it's cut using aluminum?
Can you repeat the question because we didn't hear very well?
Yeah, sure. So when you're designing drivetrains with holes for screw and bearings, how much tolerance do you want to add to ensure that the parts fit when it's cut when you're using aluminum?
So when we are when letting the space for the holes for the screws holes, we are letting a tolerance about 2 millimeters or even 1, but we don't have less than 1 millimeter.
Okay, great. Sounds good. Do we have any questions for in person? Yes. I'll bring over the mic today.
Well, there are a lot of holes on the robot. Is it that you usually use the competition for other robots and the yeah. Did you catch the question?
I don't think we can hear you very well.
That's fine. I can repeat it for you. So the question was, so there's a lot of holes on the robot. Are there any interferences with like other robot mechanisms getting stuck in it? Or yes, like that.
No, so our mechanisms are very rigid and we make sure to be this way. So they aren't interfering with other mechanisms.
Okay, great. We'll take one more question from in person. And then for others, people, you can probably join the Zoom and ask.
So, did you use a program to design? So did you use a program to design your chassis, like an AI, to help you stress test it, or did you like calculate how big and what size all of the holes inside need to be?
So we are using SolidWorks for the stress test because it has a feature where you can simulate all of the forces of the plates, and also it has many more features to include. But we mainly use only the stress test.
Nice. Thank you so much, Ro2D2. Let's all give them a round of applause for that presentation.